Welcome to our presentation on Bayesian estimation in Stata. Today, we will journey from the theoretical foundations of Bayesian statistics to its practical application using Stata 19. This guide is specifically designed for economists and researchers looking to leverage modern econometric techniques. At its core, Bayesian estimation is about updating our initial beliefs, or priors, with new evidence, the likelihood from our data, to form a more refined understanding, known as the posterior distribution. This iterative process allows us to combine existing knowledge with observed data for more robust analysis. Traditional frequentist estimation, like OLS, relies heavily on asymptotic theory, which fundamentally assumes an infinitely large sample size. However, in many real-world economic applications, such as macroeconomic analysis or policy evaluation, we frequently encounter limited data. This scarcity of data often renders p-values unreliable and leads to inflated standard errors, resulting in high uncertainty in our estimates, typically represented by wide confidence bands. The good news is that researchers often possess valuable prior knowledge, stemming from established economic theory or findings from previous studies. Unfortunately, classical frequentist models tend to ignore this crucial context. Bayesian methods offer a powerful opportunity here. By formally incorporating this prior knowledge alongside the observed data, we can significantly reduce uncertainty and achieve more precise and robust estimates, reflected in narrower credible intervals. This fundamental difference in how information is utilized is central to distinguishing between frequentist and Bayesian statistical philosophies. Stata offers a versatile suite of commands tailored to various research goals within the Bayesian framework. The specific command you choose will depend on the econometric question you aim to answer. For standard regression models, such as linear, logistic, probit, or multi-level models, the straightforward Bayes prefix is your primary tool. It can be applied to over 60 existing Stata estimation commands. If you're grappling with model uncertainty and need to determine which variables truly belong in your model, Stata 19's bmaregress command is ideal for Bayesian model averaging. When dealing with a large number of potential predictors and seeking high-dimensional selection, bayesselect offers a Bayesian approach similar to lasso. Finally, for custom or nonlinear models where you need to define the likelihood function yourself, the powerful bayesmh command, employing the Metropolis-Hastings algorithm, provides complete flexibility. On this slide, we compare the two fundamental statistical paradigms, frequentist, or classical, and Bayesian. In the frequentist framework, parameters are considered fixed, unknown constants, and our data is a random sample. Inference is based on repeated sampling, where a 95% confidence interval implies that if we repeated our study many times, 95% of those intervals would contain the true parameter. The Bayesian paradigm offers a different view. Here, parameters are treated as random variables, and our observed data is fixed. Bayesian inference centers on the posterior distribution, representing our updated beliefs about the parameter after observing the data. This leads to a credible interval, which has a more direct interpretation. There is a 95% probability that the true parameter lies within this specific range. This philosophical difference is also evident in statistical software, for example, using a standard regress command versus a bayesgraph prefix. This fundamental shift in understanding parameters and uncertainty is powered by a critical mathematical theorem, which we'll explore next. At the very core of Bayesian analysis lies Bayes' theorem, our mathematical engine for updating beliefs. The formula, as shown, states that the posterior is proportional to the likelihood multiplied by the prior. Let's break down each component. The posterior, denoted as p of theta given y, represents our updated knowledge about the parameter theta after we have observed the data y. This is the ultimate result we are seeking. The likelihood, p of y given theta, is the evidence gleaned from our data. It's the probability of observing our data given a specific value of the parameter, and it's essentially the same likelihood function used in traditional maximum likelihood estimation. Finally, the prior, p of theta, encapsulates our initial belief about the parameter theta before we even look at the data. This is where we formally integrate existing knowledge from economic theory or previous research into our analysis. For instance, if we're estimating price elasticity, our prior might be that it's negative based on theory. The likelihood comes from our sales data, and Bayes' theorem combines these to give a refined posterior estimate. Since this equation can be challenging to solve analytically, Stata utilizes powerful simulation methods, specifically Markov chain Monte Carlo, or MCMC, to draw samples from this complex posterior distribution, giving us a practical way to apply this theory. The choice of prior is a key decision in Bayesian analysis. A non-informative, or flat, prior expresses maximal uncertainty, essentially letting the data speak for itself. When using such a prior, the results will often closely mimic those from frequentist ordinary least squares, or OLS. In contrast, informative priors are employed when we have strong expert knowledge or compelling results from previous studies. These priors can shrink our estimates towards these prior beliefs, which is particularly valuable when dealing with small or noisy samples, where the data alone might be insufficient. Finally, conjugate priors are selected primarily for mathematical convenience. When a conjugate prior is combined with a given likelihood function, the resulting posterior distribution belongs to the same family of distributions as the prior, which greatly simplifies the computational process. Bayesian analysis moves us away from the binary significant or not significant thinking of traditional p-values. Instead, it allows for much more intuitive and direct probabilistic statements about our parameters. The core tool for this is the credible interval. As shown in the graph, a 95% credible interval for the return to education, spanning from 6% to 9%, means we can directly state there is a 95% probability that the true return to education lies within that specific range. This contrasts sharply with the often misunderstood frequentist confidence interval, which is a statement about the procedure over infinite hypothetical repetitions, not about the specific interval calculated. Furthermore, hypothesis testing becomes straightforward. We can calculate the exact probability of a hypothesis being true. For example, we can directly determine the probability that a coefficient, beta, is greater than 0, which might be 0.99, giving us a clear measure of certainty about the direction of an effect. One of the most powerful features of Stata's Bayesian suite is its sheer simplicity. You can transform more than 60 standard estimation commands into their Bayesian counterparts by simply adding Bayes at the beginning. For instance, a standard linear regression is run with regress, price, MPG foreign. To execute the Bayesian version of this exact model, you simply preface it with Bayes, making the command Bayes, regress, price, MPG foreign. When you use this prefix, Stata automatically combines the likelihood function from the underlying command with default non-informative priors, and then employs Markov chain Monte Carlo simulation to estimate the posterior distribution. This powerful and versatile prefix works for an extensive range of models, including logit, probit, Poisson, panel data models like XTReg, multi-level models with mixed, and even time series models such as VAR. While these defaults are convenient, you'll often want more control over the estimation process. Let's look at some essential syntax options to customize your Bayesian analyses. While the Bayes prefix offers great simplicity, you'll often want finer control over the Bayesian estimation process. This slide highlights some essential syntax options. To ensure your research is always reproducible, it's crucial to use the rseed option. This sets the random number generator seed, so you get identical simulation results every time you run your code. The MCMC size option allows you to specify the number of Markov chain Monte Carlo iterations, directly impacting the precision of your posterior estimates. The default is often 10,000, but complex models may require more. Critically, to incorporate your domain-specific knowledge or findings from previous studies, you use the prior option. Here, you define the custom belief about your parameters by specifying the shape of the prior distribution, such as a normal distribution with a particular mean and standard deviation. Additionally, options like burn-in help discard initial samples where the MCMC chain might still be stabilizing, and thinning can reduce autocorrelation in your samples, leading to more independent draws from the posterior distribution. Together, these options provide the flexibility to tailor your Bayesian models effectively. Before diving into running Bayesian models, proper data preparation is crucial. There are 3 key aspects to consider. First, you must effectively handle missing data. Similar to most regression commands, Bayesian estimation in Stata typically performs list-wise deletion, meaning observations with any missing values for your model variables are dropped. Always check your data for missingness using commands like mistable summarize beforehand. Second, for time series or panel data, it's essential to declare your data structure using tsset or xtset. This ensures that Bayesian models designed for these data types, such as bayesvar or bayesxtreg, function correctly. Finally, and highly recommended, scaling your variables can significantly improve the efficiency of the MCMC algorithm. Standardizing variables to have a mean of 0 and a standard deviation of 1 helps the chains mix better and converge faster, even though it's not strictly mandatory. The Stata example on the right shows how to load data and then create a standardized version of a variable like price. With these preparation steps complete, we are now ready to move on to running our first practical example. We're now ready to run our first Bayesian model using Stata's classic auto dataset. Our objective is to understand how car price is influenced by its miles per gallon and weight. The command is quite simple. Bayes rseed 2023, regress price mpg weight. The rseed option ensures reproducibility, so our results can be replicated. When you run this command, Stata initiates a Markov chain Monte Carlo, or MCMC, simulation. First, it performs a burn-in phase, discarding 2,500 initial samples to allow the simulation chain to stabilize. Following this, the simulation phase begins, where Stata draws 10,000 meaningful samples from the posterior distribution of our model's parameters. It's crucial to remember that MCMC is a sampling process, not an optimization method like the sum of squares minimization used in ordinary least squares. These 10,000 samples are what we'll use to build our estimates. Once complete, Stata will present the output table, which we'll interpret next. Now that our Bayesian model has run, let's interpret the estimation output. This table summarizes the posterior distributions for each parameter. The mean column represents the posterior mean, which is our primary point estimate for each coefficient, derived from averaging all samples drawn from the posterior distribution. Crucially, the MCSE, or Monte Carlo standard error, indicates the precision of our simulation itself. A small MCSE relative to the standard deviation suggests that our MCMC process ran long enough to produce a stable estimate of the posterior mean. Most importantly for inference, the 95% credible interval provides a direct probabilistic range for the true parameter value. For instance, for the weight coefficient, we are 95% certain that the true effect of a 1-unit increase in weight on price lies between $0.49 and $3.01. For MPG, with a mean of negative 49.51, its 95% credible interval spans from negative 218.44 to 119.33. Since this interval contains 0, we cannot be very certain of a non-zero effect from MPG after controlling for weight. However, before fully trusting these numbers, we must perform a vital diagnostic, checking for MCMC convergence. After running a model, it's absolutely crucial to check if the Markov chain Monte Carlo, or MCMC, simulation has truly stabilized and converged. We use the bayesgraph diagnostics command for this essential visual assessment. The first plot, the trace plot, visualizes the value of a parameter at each iteration of the simulation. A healthy trace plot should resemble a fuzzy caterpillar, showing no upward or downward trends and constant variance, which confirms the chain is stationary and properly exploring the parameter space. Next, the autocorrelation plot tells us how correlated consecutive samples are. For efficient sampling, we want to see this autocorrelation drop to 0 very rapidly, as depicted here. This indicates that our MCMC draws are sufficiently independent. Finally, the density plot displays the estimated shape of the posterior distribution for the parameter. A smooth, well-defined curve, often bell-shaped, suggests that the simulation has accurately captured the parameter's distribution. Together, these diagnostics assure us that we can trust the posterior estimates from our Bayesian model. Bayesian analysis truly excels when it comes to answering specific, practical questions in direct probabilistic terms. Instead of simply stating whether a result is significant, we can quantify the likelihood of an effect. For instance, we might ask, what is the probability that an increase in miles per gallon reduces the car price by more than $200? This translates to testing if the coefficient for MPG is less than -200. To do this, we use Stata's bayesTest interval command, specifying the parameter for price related to MPG and setting an upper limit of -200. From our 10,000 MCMC samples, Stata calculates this probability. The result, shown here, is 0.85. This means there is an 85% probability that the effect of MPG on price is indeed stronger or more negative than -200. This provides a clear, intuitive measure of evidence directly supporting our hypothesis, which is a major strength of the Bayesian framework. Often, we're uncertain about which variables truly belong in our model. Traditional methods force us to select a single best model, but this ignores the inherent model uncertainty. Bayesian Model Averaging, or BMA, directly addresses this by estimating across thousands of possible models, each with different combinations of predictors. Stata 19 simplifies this with the BMA regress command. The key output from BMA is the posterior inclusion probability, or PIP, for each variable. This PIP tells us how robust a predictor is across all these different model specifications. In the accompanying chart, we see that weight has a PIP near 1.0, meaning it was included in almost every high-probability model, making it a very robust predictor of price. Foreign has a PIP of 0.65, indicating it's a likely predictor. Conversely, length, with a PIP of just 0.05, is very unlikely to be an important predictor. This powerful technique helps us build more robust and reliable models by accounting for the uncertainty in our model selection process. A key advantage of the Bayesian approach is its power in prediction and forecasting. Unlike traditional methods that provide a single-point forecast, Bayesian prediction generates a full distribution of potential outcomes. We use the bayespredict command to simulate these outcomes, effectively creating a new dataset that encapsulates this entire predictive distribution. This enables us to construct a Bayesian predictive interval. What's crucial here is that this interval naturally accounts for two significant sources of uncertainty, both the uncertainty inherent in our estimated parameters and the fundamental random error variance. This comprehensive approach provides a much more honest and complete picture of the uncertainty surrounding any forecast, moving us beyond simple point estimates to a richer understanding of the likely range of future values. We then use bayesstats summary to analyze this predictive distribution and draw insights. To summarize our journey through Bayesian estimation, the workflow involves 4 key steps. First, we specify our model using the Bayes prefix, defining both the likelihood and any custom priors. Second, Stata simulates the posterior distribution using Markov chain Monte Carlo algorithms like Metropolis-Hastings. Third, we must diagnose the simulation's output with bayesgraph diagnostics to ensure the chain has converged and is stable. Finally, we infer by interpreting the posterior means and, crucially, the credible intervals, which allow for direct probabilistic statements. Ultimately, Bayesian analysis empowers us to answer the question we truly care about. What is the probability that my theory is true? For deeper dives, Stata provides comprehensive resources, including the Bayesian Analysis Reference Manual and the Bayesian Model Averaging Manual for Stata 19. To begin, simply type Help Bayes in Stata.